All right, let's get into it. Today, we're going to plan the ultimate road trip, but forget Route 66. Our destination isn't on any map on Earth. We're going to an asteroid, and we're going to break this wild journey down into steps that actually make sense.
So think about the last road trip you planned. You had maps, right? Gas stations, rest stops, and a destination that, stays in one place. Well, a trip to an asteroid has none of that. So how in the world do you plan a journey through the total vacuum of space to a target that's whipping around the sun? That's the incredible puzzle we're going to solve today.
So before we even pack our bags, we have to ask the most important question. Why? Why would we go through all this trouble? What's the objective of this insane journey?
Well, here's why. Asteroids are basically nature's treasure chests floating in space. They're jam-packed with the rare metals we need for all our electronics, and even better, they're loaded with water ice. Now that water is the real prize, not just for life support, but because you can crack it open to make rocket fuel in space. And listen, we already know we can get there. Missions like Japan's Hayabusa 2 and NASA's OSIRIS-REx have literally gone to an asteroid, scooped up a sample, and brought it back home. This isn't science fiction anymore.
Okay, so we've got our destination and we've got our motivation. So let's start phase 1 of our cosmic road trip, just getting off the ground.
To break free from Earth's gravity, to climb out of what scientists call its gravity well, you need a truly ridiculous amount of energy. The magic number is called escape velocity, and for us, that's a mind-boggling 25,000 miles per hour. The only way to get that kind of big push is with giant, powerful chemical rockets, like the NASA SLS you see right here. They are our ticket off this rock.
But here's the catch. You can't just light the candle whenever you feel like it. Timing is everything. See, Earth and our target asteroid are both hurtling through space on their own tracks. To save a ton of fuel, you have to launch in a very specific, very narrow launch window when everything lines up just right. The analogy is perfect. It's exactly like catching a bus. And if you miss it, you're not just going to be late for dinner. You could be stuck waiting years for the next one.
All right, we did it. We escaped Earth's gravity. We're in space. Now comes phase 2, the long cruise. So, how do we keep this thing going for millions and millions of miles?
So, the fundamental challenge of deep space travel boils down to this one simple trade-off: thrust versus efficiency. Raw power on one side and fuel mileage on the other. It's like choosing between a drag racer and a hyper-efficient hybrid. You can't have it all, and the choice you make here defines your entire journey.
First up, we have our chemical rockets. These are the sprinters of the solar system. They give you an unbelievable amount of thrust, which is exactly what you need for that initial punch to escape gravity. But they are absolute gas guzzlers. They burn through their fuel way too fast to be practical for a cruise that could take months or even years.
And that's where the tortoise enters the race, the ion thruster. See, instead of a big, violent explosion, this thing uses electricity to shoot out charged particles, creating this super gentle but constant push. We're talking a thrust that's about the weight of a single piece of paper. But here's the magic. Its fuel efficiency is off the charts. NASA's Dawn mission traveled nearly 6 billion kilometers on just 425 kilograms of fuel using these engines. That's how you win the marathon in space.
Now for something that is straight out of a science fiction novel, solar sails. These are the gliders of space travel. They have no engine. They carry zero fuel. Instead, these massive, paper-thin sails actually catch the pressure from sunlight itself, the tiny push from particles called photons, to move. Now, the acceleration is incredibly slow, but over time, since you never, ever have to refuel, they're an amazing option for long-haul scouting missions.
So let's just recap real quick. We've got the sprinter for the launch, the jogger, our ion drive, for the long cruise, and the glider for fuel-free scouting. But here's the key takeaway. You don't pick just one. The smartest play is a hybrid strategy. You use the brute force of a chemical rocket to get off Earth, and then you switch to a super-efficient ion drive for the long, quiet journey to the asteroid. It's the best of both worlds.
Okay, we've got our engine strategy sorted. But how do we steer? There are no road signs in space. So let's enter phase 3, cosmic navigation.
The very first rule of navigating in space is you have to forget everything you know about straight lines. Trying to go from point A to point B directly is a colossal waste of fuel because gravity is constantly bending your path anyway. The real goal isn't to travel the shortest distance, it's to conserve the most energy by riding the natural curves of this cosmic highway.
So, the most famous route on this highway is called the Hohmann transfer.
is this beautiful, elegant orbital path that uses just 2 short engine burns to hop between orbits. The playground analogy is just perfect. It's like giving a little push at the bottom of a swing and letting your momentum carry you the rest of the way up. It's the most fuel-efficient route possible, but the trade-off is that it completely depends on hitting those super precise launch windows we talked about earlier.
Now, if you want to be even more efficient, and you're not in a hurry, you can use what's called the Interplanetary Transport Network. This system uses these special stable points in space where gravitational forces cancel each other out, creating these tunnels that let you travel using almost zero fuel. It's like catching a cosmic ocean current. Now, the trip takes years instead of months, but it's the absolute perfect way to haul heavy cargo when time isn't the biggest issue.
Of course, this trip isn't a walk in the park, it's full of hazards. As soon as you leave the protection of Earth's magnetic field, your spacecraft is just getting pummeled by high-energy cosmic rays. This radiation can literally fry sensitive electronics, so building in robust shielding isn't a luxury, it's absolutely essential.
Then there's the communication lag. You just can't fly a spacecraft with a joystick when it takes 20 minutes for your signal to even get there, and another 20 minutes to see if it worked. For those supercritical moments, like, say, landing on the asteroid, the spacecraft has to be smart enough to make its own decisions. And this is where autonomous AI becomes a complete game changer.
And finally, you get there, and you have to deal with microgravity. Landing on an asteroid isn't like landing on the moon. You're trying to dock with a tiny, spinning, basically weightless rock. If you just touch down, you're going to bounce right off into space. You have to actively anchor yourself to the surface, using things like harpoons and drills to literally grab on and hold tight.
So let's take a breath. We've covered how to escape Earth, how to cruise through deep space, and how to navigate these cosmic highways. And you know, despite all the hazards, it seems like all the major pieces of this puzzle are actually ready. And this right here, this is the idea that makes this whole thing sustainable in the long run. It's called in situ resource utilization. Instead of dragging every last drop of fuel up from Earth, you go to an asteroid, you mine the water ice, you use solar power to split it into hydrogen and oxygen, and you create rocket propellant right there. You create a gas station in space. This is how you build a real economy out there among the stars.
And that's really the big takeaway from all this. The fundamental toolkit is ready to go. We have the powerful chemical rockets to escape. We've got the hyper-efficient ion engines for the long cruise. And we have the cosmic maps, the navigation techniques, to get there safely and efficiently. All the essential pieces are already on the board.
We've got the vehicles, we've got the maps, we have the destinations just waiting for us. The technology to open up this brand new frontier exists right now. Which really just leaves us with one final, very powerful question. It's no longer a matter of how we'll get to the asteroids, it's just when.